Hello, y'all. Welcome to lesson 116 of my DP chemistry curriculum. Today we're going over structure 3.2.1. We're beginning organic chemistry. So this states that organic compounds can be represented by different types of formulas. These include empirical, molecular, structural, full and condensed, and stereochemical and skeletal. So we're going to go through all these types of formulas. Now, we'll be able to identify formulas and interconvert molecular, skeletal, and structural formulas by the end of this unit. And we'll be able to understand 3D models with real or virtual of organic molecules. Now, for stereochemical formulas, you're not expected to draw them except where specifically indicated, and that specific indication, I'll say right now, is in HL chemistry, talking about cis and trans isomerism. So if you're in HL, make sure that you are pretty comfortable in this. If you're in SL, you just need to understand what you're really doing here. So with that out of the way, what is organic chemistry? So organic, people often think of as like pesticide free, and we think about that in terms of food. But when we're talking about chemistry, organic really is the branch of chemistry that just focuses on carbon molecules. Now, the very specific thing is organic just means containing carbon and usually also hydrogen and sometimes oxygen, but mostly carbon and hydrogen. Now, because there is so many different ways that carbon can bond, uh, which we call catenation, which we'll talk about in a little bit, we have to know that along with organic chemistry, we have to really learn about the comprehensive naming system. Now, this naming system, which is often referred to as the IUPAC naming system, standing for International Union of Pure and Applied Chemistry. The IUPAC naming system is the way we reference all organic molecules. And this is actually one of the most challenging parts of organic chemistry. This is what students usually struggle with most, is just naming them to know what they're looking at. So this is something we're going to focus on in a later video, but not this one today. Today, we're going to talk about how to draw compounds and the different formulas. Now, furthermore, something that we just want to get ahead of and put in our brain is that we often classify organic compounds by their properties. Now, their properties, being both chemical and physical, are a lot easier to see when the molecule is drawn and based on the formula you're provided. So we're going to talk about that. Now, going back to what I mentioned, is why is carbon special? Why carbon? Well, carbon's really important because first off, it makes four bonds, or it can make four covalent bonds. Now, because of the many bonds and many ways it can bonds, which we refer to as catenation, referring to the many ways it can bond, it becomes special in that it can form many different molecules with many different properties that serve many different jobs, even with the same exact molecular formula. So what do I mean by this? Well, first off, we have three different types of structures it can make. It can make straight chain structures, straight chains. Something you might see for a straight chain structure just might be a series of carbons. You'll note I'm not drawing any other atoms, but just single bonded to each other, maybe a double bond thrown in there, maybe even a triple bond thrown in there. But we can just bond in a straight chain. We can also form branched chains. Whoops. And just like it sounds, we have our straight chain, but on top of our straight chain, we may have a bond to a carbon above, a bond to a carbon below, maybe another carbon thrown in there, maybe another carbon bonded. So we have our straight chain, but because carbon can make so many bonds, we can branch those chains off. Just going to move this one right here. Oh, just so that in the PDF version of these notes, it is not cut off. Now, lastly, carbon can even form what we call ring structures. You might have a four carbon ring This is usually not too stable, but it can be. We have 5 carbon rings. One of the most famous 5 carbon rings, if we throw an oxygen in there, actually shows up in our DNA. That's our pentose sugars and our RNA. And we have 6 carbon rings, which these are pretty much all sugars, but also things like graphite and graphene use 6 carbon rings. Um, so these ring structures are very, very important to organic chemistry as well. And so we need to identify that carbon can make any of these structures and even combinations of these structures when forming larger molecules. So that's what makes carbon so special. So when we're discussing how to draw this, or write this out, we have many different formulas. So far, we know empirical formulas, empirical, and molecular. Now, with catenation of carbon, these do not describe everything. So with catenation, these cannot fully describe organic compounds. You might be saying, well, what do you mean? And I'll show you with a quick example. So let's take the formula C4H10. Now, because it's simplified, or not simplified, you know that this is likely a molecular formula, and it is. I can do the empirical of C2H5, and I can go ahead and even draw something similar to a Lewis diagram of this. Now, if I were to draw a Lewis diagram, and I just take a nice straight chain of carbons, and I bond a hydrogen to each, here is our C4H10. This is a compound known as butane. And you've probably heard of butane. There's like butane lighters, and we use it for a lot as a fuel. But the thing is, because carbon's so special, it can form a different compound with that same formula. And this you may also note as C4H10. But not only is this completely different, it has different properties, different chemical properties, different physical properties. And this one is called methyl propane. These names, of course, coming from the IUPAC naming system, which we'll cover in a later video. So we need something else to differentiate our organic compounds. What I've done right here is drawing these out. While they may look like Lewis structures, these are actually what we call full structural formulas. So it's not an empirical formula, it's not a molecular formula, it is a full structural formula. Now, this gives the most info of any given organic compound. And like I said, it's similar to a Lewis structure. But the main difference here is that we do not draw unbonded electron pairs. So all our unbonded electrons are not drawn. Now, in this case, all of our electrons are bonded, but an example might be if we have oxygen bonded to hydrogen, bonded to something, I'm going to say R. I'm not going to draw the electrons on oxygen. This is just not necessary. And so I'll do a little vice versa of this right here. R, O, H. So here's our Lewis, and here's our full. So non-bonded electrons are not shown. Now, this is very helpful for us to be able to see the entire picture of the organic compound. But we actually have a couple other ways to write it when we don't want to draw a structure every time. What if we don't want to show the bonds? Well, we can also do a condensed structural formula. Now, for our butane, our condensed structural formula, which I'm going to say omits bonds. So for butane, it may just look like CH3, CH2, CH2, CH3. So when I go ahead and look up here, I can just count that out. CH3, CH2, CH2, CH3. Now, for methylpropane, on the other hand, I might do CH3, CH, in parentheses, CH3, 2. And that tells me I have CH3, CH, and then 2 CH3s attached to that. So we can write this in various ways, these parentheses indicating that both of these are their own individual ones attached to that carbon. So the condensed structural formula helps us write things out a little bit faster. Now we're going to get to my favorite right here, which is the skeletal formula. Skeletal formula pretty much just shows carbon backbone. It's very quick to draw and indicate everything you need. And it also shows bond angles, usually. It's the most accurate in terms of bond angles without doing a stereochemical formula. Now, lastly, the only atoms shown are part of functional groups. And we'll describe what functional groups are later, but it helps us classify different types of compounds. So for butane, it just looks like this. This is the carbon backbone of butane. I'll go ahead and label these as well. Oops. You can indicate that there's a carbon, 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 along with their bonds. We don't show hydrogens, we don't write them out. For our methylpropane, very similarly, it looks like this. We still have our carbon, 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 no hydrogens shown. Once again, that is our methylpropane. So I prefer skeletals mostly because they're fast to write, they show all the information I need, and you get used to it pretty quickly. So the best way to work on this is let's just go ahead and do some practice. So let's start with ethanol. Now I'm going to draw this out and I will write what's required. And then you may want to pause the video and try it yourself, though you can likely figure out what I'm going to be asking. So here is the full structural formula. What we need to try doing is writing the empirical, molecular, condensed structural formula, and lastly, skeletal. Now, for skeletal, I'll let you know right now, this OH is an alcohol functional group. So this itself as a functional group should still be drawn because we only show atoms part of functional groups. So go ahead, pause the video, try it yourself. I'm going to go ahead and write the answers right about now. The empirical is C2H6O, which is similar to the molecular C2H6O. The condensed is going to be CH3, CH2, followed by an OH. Lastly, the skeletal is going to look like this. OH. You'll note that I still have one carbon, two carbon, but now this carbon is bonded to something we are drawing. So we draw that OH because once again, as I mentioned, it is a functional group. Given that, let's go ahead and try a new compound. This one's going to be called butanoic acid. Butanoic acid. And it is C with 3 H's. You may recognize I've used the term bute now a couple times, and that usually represents 4 carbons. Bute is our IUPAC prefix for 4 carbons, especially when they're in a straight chain. So once again, we're going to look for the empirical, skeletal, molecular, and condensed. So I'll put this right here. Go ahead and pause the video, try it out yourself. I'm going to start writing the answers now. I usually like to start with the molecular formula before I go to empirical, and that's because I can see what the full thing is. C4H8O2, meaning I can just divide by 2 to get C2H4O. My condensed is CH3, just reading left to right, CH2, CH2, COOH. And then lastly, my skeletal is going to look almost exactly like butane. But now that I'm here, I have to do a double bond to an oxygen and a single bond to an OH. And there we go, butanoic acid. Like I mentioned before, we can even see the bond angles. Right here, we notice a bond angle of about 120 degrees, which does represent the molecular geometry around that double bond, or this trigonal planar electron domain geometry around this carbon atom. All right. So those are the main formulas we're going to be using throughout organic chemistry, but we have one more that we want to focus on just for a moment, and that's called the stereochemical formula. Stereochemical formula. Stereochemical formula is mainly to represent 3D. 3D nature of organics. And it uses a couple different ways of drawing because this is a drawn formula. So we use this shaded in wedge, and we call this a tapered wedge. And what that's going to do is that's going to be representing coming out of the plane of the paper, or in my case, an iPad or whatever, but it's coming out. It's 3-dimensionally leaving the paper. We have a dashed wedge. That is going behind the plane, going behind the plane of the paper to kind of like push back behind it. And then lastly, we still use straight lines. Now, these all are used to represent bonds. Very specifically, these are used to represent any bond of 2 electrons being shared between an atom. And this is just in the plane of the paper. So if we were to write a full structural formula of methane, which is just CH4, which you should be familiar with at this point as a common name, this doesn't actually show the geometry because here, this looks like 90 degrees, but it can't be. We know it's supposed to be 109.5. So how do we represent that? Well, if I draw my 3-dimensional one, I now have this bond angle of 109.5. And now I need something coming out of the paper because this is a tetrahedral shape. So I will do my wedge. And that's coming out of the paper. And my dashed line. And that is going behind the paper. And there you have it. This is our stereochemical formula. Hopefully this is going to help you get a little more acquainted with pictures and images we're going to be drawing throughout this unit. Make sure you have these formulas down so that once we start adding functional groups to them, you can start identifying these very quickly. So hopefully this helps, and have a great